do it. Very happy to have Angus back, who's going to tell us about how to prove Riemann hypothesis.
Very heavily parenthesized addendum to that remark. Yes, but hello again, friends. No, actually, I'm not going to start like that. I'm not going to be presumptive. I'm not going to be too presumptuous. So, hello again, friends and enemies. Much better. All right. Today, we're going to prove the Riemann hypothesis. How hard could that be? So, last time we talked about getting some nice examples under our belt for the Weil conjectures, and we looked at the case of elliptic curves. We talked about elliptic curves in general, and then we saw some sort of numerical examples that suggested what form the Weil conjecture should take for those elliptic curves. And we proved absolutely nothing. So today we'll try and rectify part of that and provide some proof for various statements. Not going to prove every detail. Some things will go unsaid, but hopefully it'll be at least persuasive. And hopefully there'll be enough references that you can track down the statements that you'd like to understand and read them yourself if you would like more details. As always, interrupt me throughout. Feel free to unmute yourself and just talk or post in the chat. I can see it all. We should be good to go. So yes, last time, click on the right thing. So last time we introduced the idea of an elliptic curve. So an elliptic curve is a variety defined over a field. In particular, it's a one-dimensional variety, a curve, and it's projective. It lives inside projective space. In fact, it lives inside two-dimensional projective space. It's what's called a plane curve. And it can be given by a cubic equation, and part of the data is that we pick a base point. And it turns out, if the characteristic of your field is not 2 or 3, you can always make a change of variables to put it in this nice form called the short Weierstrass form. And smoothness is this particular condition on the coefficients a and b. We discussed that, in fact, elliptic curves have this remarkable property. They inherit a group structure. They're, in fact, the only one-dimensional projective varieties that have group structures. In that way, they become examples of abelian varieties. And what we said is that, okay, an algebraic group means an algebraic variety with some sort of morphisms of algebraic varieties that behave like group operations. One other way to package that information is to say, okay, well, given a variety, I can look at its points over any field. I can look at the set of solutions to the equation over a particular field. That's a set. And being an algebraic group means that every one of those sets actually has the structure of a group. And it is more than just that data. You have this sort of nice compatibility between the different fields, but that is one way to think about it. You can think about it as a collection of groups for each field that you would plug into your equation. All right, so that is elliptic curves at large. We looked at them over the complex numbers, and we looked at them over finite fields. And over finite fields, we had our zeta function, this generating series of the point counts over various finite fields. And after doing some experimentation, we came to a certain form of that zeta function, and we discussed whether or not that satisfies the expectations of the Weil conjectures. So let's look at what that zeta function was. I should correct something. I think last time I was writing plus AQ in this numerator of the fraction here. I'm now writing it as minus AQ to go along with the sort of standard notation. So we did some examples last time. We computed some point counts. We computed some power series and noticed that actually, once we sort of took out the right factors, we were getting things that look like rational functions. And for an elliptic curve over a finite field FQ, we said that the zeta function of the elliptic curve was this particular rational function. The numerator was a single quadratic, 1 minus AQT, where AQ was some quantity, and Q is the cardinality of the base field. And then the denominator had these two linear factors. What was AQ again? It was the difference between the point count of E over FQ, the rational points over the base field, the difference between that and 1 plus Q. We said those two should be kind of similar because there's a heuristic argument why we expected the point count to be around 1 plus Q, and then this AQ is measuring the difference, the error of that. And we checked, what does this do in terms of satisfying the Weil conjectures? Well, first of all, yes, it's a rational function. Second of all, if you just plug in the functional equation, you get exactly what you expect. In this case, you just expect if I replace t with 1 over qt, it should be the same thing, and indeed that holds. We wanted to check the Riemann hypothesis, the fact that these two roots of that quadratic, w1 and w2, are both of absolute value square root q. And that's not obvious just from looking at this. Certainly their product is q, but that doesn't tell us that each of their absolute values is square root q. So there's something to be said there. And then finally, it does satisfy the expectation we had about the Betti numbers. The Betti numbers are exactly 1, 2, and 1, which are the degrees of our polynomial factors. So we need to do two things. First thing, we need to take our generating function, our zeta function, and make it look like this rational function. We need to write our infinite series and explain why it looks like a rational function. That's step one. The Riemann hypothesis is a distinct step. That is something we're just going to have to do separately. Once we get that the zeta function looks like this, everything is done except the Riemann hypothesis. So those are the two steps. Prove the zeta function is of this form, and then prove the Riemann hypothesis. So that's the plan for today. This will involve taking a walking tour of the sort of theory of elliptic curves, discussing many things we didn't get to last time, and not devoting nearly enough time to any of it. So I do highly encourage you to spend more time with these ideas. It's a beautiful theory, and we're only going to really scratch the surface of it in terms of aiming towards our goal. At the end, once we have gotten to the proof, I'll talk a little bit about how the ideas of this proof might work in a more general setting. How many of these things generalize, or what would you need to introduce to generalize these things? And then I'll also talk a little bit about like some applications of this. What do the Weil conjectures actually buy you in things that people are trying to use them for? All right, cool. So let's try and get to this. Why should the zeta function of an elliptic curve equal a rational function? Well, let's just write these two things as equal and just do some rearranging and see exactly what we're asking for. So this is the equation that I want to be true. The zeta function of the elliptic curve, which by definition is the exponential of this power series on the right, should look like this rational function on the left, where in the middle, I've factored the numerator quadratic into two linear terms, w1, w2 being the reciprocal roots. Now, I'm going to take log of both sides and do some rearranging, and then I'll look at matching up the coefficients. So taking log of the left-hand side, well, we split up the log over the products and quotients, and we get these sums and differences of logs of each of these linear terms. Log of 1 minus w1t, log 1 minus w2t, log 1 minus t, log 1 minus qt. And each of those can be expanded with its usual power series expansion around 0. So in each case, log of 1 minus x is x to the m over m. So all we have to do is replace x with whatever we have here, w1t, w2t, t, and qt. Oh, we have a minus sign at the front as well. So the first one is minus the infinite sum of w1 to the m, t to the m over m. Same with w2, same with, well, just 1 to the m, and q to the m here. And now I can just add these all up and have the single coefficient of t to the m over m being 1 plus q to the m, coming from these last two terms, minus w1 to the m minus w2 to the m. So this equality, the zeta function of the elliptic curve equaling the desired rational function, is equivalent to showing this. It's equivalent to showing that the number of points of our elliptic curve over the finite field of size q to the m is precisely given by a formula like this: 1 plus q to the m minus w1 to the m minus w2 to the m, where w1 and w2 are complex numbers whose product is q. Once we have that, that will show us that the zeta function has to be of this form. So that's what we want to do. We want to count the points in the elliptic curve, get a formula like this, and from that, we will be able to then deduce the expression for the zeta function. So this is the expression we're going to focus on from now on. 1 plus q to the m minus w1 to the m minus w2 to the m. That is the expression we'll be looking at for essentially the rest of the talk. Okay. So what is this expression? Where did it come from? How would we get something looking like that? Well, what I want to do is just make a sort of observation about how you might get an expression of this shape. Where would an expression of this shape come from? And it might come from a little bit of linear algebra. So I'm going to imagine we have some 2x2 matrix F. It's just normal 2x2 matrix, A, B, C, D. And given a 2x2 matrix, we can calculate its characteristic polynomial. So let's imagine that we had a matrix whose characteristic polynomial was, well, nearly the polynomial we wanted, but maybe the t is the other way around. So I'm just going to go back to the previous slide for just a moment. So on this slide, we have 1 minus aqt plus qt squared. On the next slide, well, it's almost the same. We've just put the t squared over here rather than next to the q. We'll just reverse the order of the coefficients. But it's essentially the same sort of characteristic polynomial. And now w1 and w2 are actually the roots of this polynomial rather than the reciprocal roots. Okay, so imagine we had a matrix with this characteristic polynomial. What would happen if we looked at the characteristic polynomial of the mth power of that matrix? What would happen is, well, I raise the mth power, so the eigenvalues are just raised to the mth power. I'm just applying them m times. So the characteristic polynomial of the mth power is just the product of these two linear factors, lambda minus w1 to the m, lambda minus w2 to the m. Expanding that out into a quadratic, we get lambda squared minus w1 to the m plus w2 to the m times lambda plus q to the m. And suddenly, if you were to just plug in lambda equals 1, i.e., compute the determinant of just the identity minus f to the m, we get 1 coming from that plus q to the m minus w1 to the m minus w2 to the m. This is exactly the sort of expression we wanted. This is exactly the expression we're hoping to get for the point count of our elliptic curve. So one approach might be to say, okay, can we find some sort of linear algebraic gadget, some vector space, some module with some operator acting on it that in some way is related to the point count? Can we find some linear operator on a vector space or module who spits out the correct characteristic polynomial, and somehow this determinant is connected to the point count of an elliptic curve? So that's the goal. So, as usual, to think about how might you attach some linear algebraic data to an elliptic curve, we might start with a case of a complex elliptic curve and see if we can deduce something via analogy. So for a complex elliptic curve, is there some sort of linear algebraic information associated with it? And naturally, the answer is yes. Recall that in the case of complex elliptic curves, we said they always looked like some sort of lattice. The complex numbers modulo some lattice, a rank 2 Z module. Now, last time we said it can be any two numbers, omega 1 and omega 2, as per this diagram that we saw last time. In fact, for simplicity, one can always rescale it because it's clearly, okay, I shouldn't say that. I have a personal tirade against using the word clearly. So one can see that it's okay if we scale everything by a non-zero complex number. That won't change anything. That's an isomorphism. So if this is omega 1, omega 2, I can scale omega 1 and replace omega 2 with omega 2 over omega 1, and I will get the same elliptic curve. And then if this isn't the upper half plane, just take the negative of it, because that's just a different basis for the same lattice. So we can always arrange it where our lattice is just z plus z times tau, and that will give us an isomorphic elliptic curve. Not a big deal. We won't really be using that today, but it's a nice observation. And if you've ever wondered a bit deeper about modular forms, often being presented as functions on the upper half plane, this is one of the reasons why they are useful, because elliptic curves are determined by a point in the upper half plane. So all myriad connections happening here. So this is a linear algebraic piece of information that's naturally associated with our elliptic curve, this lattice inside the complex numbers. Clearly a linear algebraic piece of information. And in fact, if you like, this can be viewed in another way. We can view this as the first homology with integer coefficients of that complex elliptic curve. That is another way to extract this lattice. Okay, so we have a piece of linear algebraic information, and we said we wanted to find some nice operator on it that's somehow related to counting points in the elliptic curve. Well, if I just give you two rank 2 lattices, I can write down any matrix sending the basis vectors to some combination of other basis vectors, and that will give me some map. So the linear maps between two lattices are just 2 by 2 matrices with integer coefficients. But we don't just want maps of the linear algebraic data in abstraction. What we want is maps of elliptic curves that are related to these maps of lattices. So do these maps of lattices always come from maps of elliptic curves? Do they induce maps of elliptic curves? How do we relate those two things? So the next bulk of the talk is going to be about maps between elliptic curves. And then we will come back, we'll cycle back to this question of what sort of information do we get on various linear algebraic information once we have a good theory of maps of elliptic curves. So sticking with the complex picture, so we've got C modulo a lattice. How do we get a map between two different elliptic curves? Well, the thinking is that, recall last time we said, when we think about complex elliptic curves, we're thinking of them as complex Lie groups. So what sort of maps do we get between these complex Lie groups, where the addition structure, the group structure, is just addition of complex numbers? What's allowed as maps of Lie groups? Well, with some thought, the only ones that'll preserve the structure that we care about are precisely the maps induced by scalar multiplication of complex numbers. So I can map from C to C just by scalar multiplication by any complex number. So I have two elliptic curves, E1 and E2. They each have some associated lattice. So E1C is C modulo lambda 1, E2C is C modulo lambda 2. And I can map from one to the other via Z maps to alpha times Z for alpha some complex number. So that's a map from C to C. To get a map from E1 to E2, we need to require a little more. We need to demand that the image of lambda 1 after multiplication by alpha lands in lambda 2. That's just to make sure the map is well defined. So the scalar multiplication map must take lambda 1 into lambda 2. Maps of this form between elliptic curves are called isogenies. And while I won't get massively into this right now, if you fix two lattices, you will find there are not many maps between them. It's a fairly controlled quantity, what is possible in terms of the homomorphisms between a pair of elliptic curves. There's a lot you can say about isogenies beyond just here are maps that there are. One important observation is that, well, okay, on one hand, we might have the zero morphism. Everything goes to zero. That's allowed. But if it's not zero, then this scalar multiplication map is a surjective map with finite kernel. Only finitely many things can map into this lattice under this restriction, and everything is going to get hit. Because if it's non-zero, you can just invert it. You can find a pre-image. So these isogenies are necessarily surjective with finite kernel. It's a nice thing to note. Now, I said that for a random pair of lattices, you wouldn't expect to see very many isogenies. But one example, or sort of class of examples of isogenies, are the multiplication by n maps. So what if alpha is not just a complex number, but specifically an integer? N is an integer. Then we get the map multiplication by n. So it's exactly the same thing. Take z to nz. Because lambda is a lattice, if x is in lambda, then nx is also an element of lambda. It's closed under scalar multiplication by integers because it's an abelian group. It's a z module. So these will always give you nice isogenies from elliptic curves to itself. So there's an example of a collection of isogenies. In fact, these are called endomorphisms because it's a map from elliptic curve to itself. So these isogenies are called endomorphisms. One thing I should say is that depending on sort of the author, the presenter, sometimes people will deny calling the zero map an isogeny. I have sort of not. I've allowed the zero isogeny, but some people would say no, isogenies have to be surjective with finite kernel, so the zero map is not an isogeny. The constant map doesn't count. It's a different kind of map, and that's fine. And I think that's standard in many texts. So do keep an eye on that. If you do happen to be reading about this somewhere, keep an eye on whether or not the zero map counts as an isogeny. I would say in general, you should expect that the standard terminology is that it does not count as an isogeny. So keep that in mind. But anyway, for endomorphisms from an elliptic curve to itself, we get the multiplication by n maps. And again, not many others. You can think about this. It's an interesting exercise. Think about what could be possible. If I want to map, if I want to have some lattice, which remember, you can always write as z plus z tau for tau an element of the upper half plane. How many complex numbers are there such that when you multiply every element of that lattice by that complex number, you stay inside the lattice? You'll find that it's very restrictive on both the complex number and the lattice itself. Many lattices will not admit anything besides these multiplication by n maps. All right, so this is the world of isogenies of elliptic curves. And again, as I said, these are all over the complex numbers. But, as is often the case, we will use this as inspiration to look at isogenies in general, maps between elliptic curves over any field. All right, so we worked out what we want our maps to be by saying we want our maps of complex elliptic curves to be maps that preserve the structure as a complex Lie group. We've noted that the important thing about elliptic curves, or an important thing about elliptic curves in general, is that they are algebraic groups. So we will ask for something similar when we look at isogenies at that level of generality. So let's move on to that. Isogeny is an arbitrary characteristic. So we've now got an elliptic curve over any field in the world. So E is just some cubic equation over a general field. And we define an isogeny of elliptic curves to be a morphism from E1 to E2 of algebraic groups. So it has to be a morphism of varieties that plays nicely with their structure as an algebraic group. So one way to say it is the coordinate function is given by rational functions of the variables, and it preserves the group structures from one to the other. Now, this might sound very restrictive, and it certainly is, but remarkably, elliptic curves are so rigid that you can get something being an isogeny much easier than this. It turns out if you have a map of elliptic curves that is a map of varieties, an algebraic map, that also sends the origin point of one to the origin of the other, then that immediately is forced to preserve the group structures. All you have to check is that 0 goes to 0. By 0, I mean the point of infinity, our origin of the group structure. But as soon as the origin goes to the origin, the identity goes to the identity, you have to preserve the group structure. It's quite remarkable. So sometimes you'll see in places people define isogeny as an algebraic map that sends 0 to 0. And a self-isogeny, an isogeny from an elliptic curve to itself, is called an endomorphism. And again, a little careful, people often would not say the 0 map is an isogeny, but the 0 map is certainly an endomorphism. That's acceptable. And again, maps from elliptic curve to itself, what are there? Well, we always have the multiplication by n map. Because remember, we have this commutative group structure. So it makes sense to act on this by an element of the integers. You just say add a point to itself n many times. And because you're abelian, this is a well-defined action of z on your object. So we get multiplication by n maps for all integers. And again, not many more. You don't expect in general to see many other endomorphisms besides those over general fields. In special cases, we will see that, in fact, there are more, but often you wouldn't expect to see many more. And once again, discounting the zero map that sends everything to identity, all of these maps are surjective with finite kernel. Now, a really important notion is the degree of an isogeny. So this can be defined in many ways. The way I'll define it is I'll think about these coordinate functions. So x1, y1 goes to x2, y2 via some rational functions. And I'll define the degree of an isogeny to be the maximum of the degrees of the rational functions in those coordinates. Now, this can be defined in other ways. If you're familiar with function fields, a map of elliptic curves induces a map of function fields, and that will establish some relative extension of fields. And the degree of the isogeny is precisely the degree of that field extension. That's another way to see it. And then we have this really nice property, which I'm not going to go into in great detail, but there's a feature that an isogeny can have being separable. If an isogeny is separable...
Sorry, Angus. So these
yes, please.
Examples that you define, they have degree n, hopefully.
Good question. No, they don't. They do not have degree n. The multiplication by n maps have degree n squared, in fact.
Okay.
Yeah. So I haven't reproduced it, but if you go back to the slides in the previous talk, you will see that I explicitly wrote out the rational function of multiplication by 2, and you get a degree 4 map. So yeah, so I should say, that's a very good point. The degree of the multiplication by n map is in fact n squared. That might sound bizarre, but we'll see that it's exactly what we want. Now, the other thing I was going to say is that the degree is closely related to the size.
I guess what's going on is that you have a 2x2 matrix that you're taking a determinant. Does that make sense? So you have multiplication by n, and you're taking determinant, so it's becoming n squared.
Yes, that is so. That is in fact exactly. That's not just a heuristic reasoning. That is exactly what's happening. We will see this precisely in the case of complex elliptic curves. That it's exactly, if you think about what multiplication by n is doing, it's sort of like an n squared to 1 map, because how many things end up inside the lattice? Well, we'll see a picture later, so this will be very explicit. And then we will see that over general fields, actually something very similar is true. There's no lattice in that case directly, but there's some sort of linear algebra object where the multiplication by n, or any isogeny, its degree is closely related to the determinant of some sort of matrix. So yeah, you're absolutely right, Masood. That is exactly what's going on. Thank you. I'll pause, Jed, before I finish what I was about to say. Are there any other questions, comments? I can check the chat. Isogeny, same genus. Isogeny, equal in kind or nature. Oh, cool. Yeah, I guess I didn't know. I didn't know the etymology of the word isogeny. That's a good point. All right. So yeah, I use this phrase like n squared to 1. And these are group morphisms. You might hope that if I wanted to calculate the degree or the the n to 1 nature of the map, then I could do that by calculating the size of the kernel. So the kernel is some sub-object of our elliptic curves. For the experts, it's a subgroup scheme. And you can talk about its order in that sense. But the important thing to notice is that, like any elliptic curve, like any variety, I can look at the points of this object. I can plug in a field of interest, let's say the algebraic closure of my field K. I can say, okay, well, what is the set of points here? So this is some set. It's in fact a finite set. And if the isogeny has a special property called being separable, then the size of this finite set is precisely the degree of the isogeny. Now, separable is a sort of niceness hypothesis. It's related to the idea that you write down a certain derivative and you ask it to be not uniquely zero. Severability is only an issue that really comes up in positive characteristic, which unfortunately is exactly the characteristic that we're interested in. In characteristic zero, this is not an issue. Everything is separable, but you can, in positive characteristics, have inseparable morphisms. So we will have to concern ourselves with that at some point. But if it is separable, then the degree is precisely the number of points of the kernel. Cool. All right. Now, I have only provided examples of isogenies by telling you about the multiplication by n maps. That's all the ones I've told you about so far. Are there any others? There are. Let me give you an example of a different isogeny in the case of positive characteristics, specifically in the case of a finite field.
So Angus, just a question. I guess another way of looking at this is that, as you said, elliptic curve is a torus. So we're looking at maps, kernels of group homomorphisms between tori. And so torus is S1 times S1. So and a subgroup of S1 is, non-trivial subgroup is finite. So then we just need to show that the two S1s give us the same size subgroup, right? To get this n squared.
Yes.
Is that clear from why that should be the case for a homomorph?
Yeah. So we can discuss this a bit. So in the complex case, I mean, one way you could see this is if you looked at sort of like the nested chain of subgroups. So if I look at the kernel of the multiplication by n map, everything that's killed by multiplication by n, I could compare that to the multiplication by 2n map. So if something's killed by n, it'll be killed by 2n. And so what you get is this sort of like, you can calculate the order of each of these subgroups. And you can say, okay, well, like, because as I said, you can write.
Okay, so it's like groups of nth root of unity in each S1. That's
exactly right.
Looking at. Okay.
Yeah, that's a perfect way to think about it.
And do we need to think about isogenies beyond these ones, these sort of analogs of multiplication by n? Do we need more than that?
Yes, we do. Okay. You set me up perfectly there. Yes. The very important isogeny that I want to discuss next is an example of an endomorphism. It's an isogeny from an elliptic curve to itself, which is not just a multiplication map. This is the Frobenius endomorphism in positive characteristic. Well, as again, specifically over a finite field. So what ends up happening is that in positive characteristic, one has this very remarkable relation. We know that if I raise something to a power, that's a multiplicative map. Xy to the p is x to the p, y to the p. But more strangely, in positive characteristic, it's also an additive map. X plus y all to the p is x to the p plus y to the p. This is something called the freshman's dream. And it's not a deep thing. Simply expand it out and notice that if I expand out and look at binomial coefficients, well, all the middle ones divisible by p. So in positive characteristic and characteristic p, those are exactly zero. Another interesting thing about this map raised to the power p is that if I take any element of fq bar, so the algebraic closure of fq, so this is so x may be in fq, it may be in some extension, it may satisfy some polynomial relation over fq. Turns out that if this element x satisfies the property that x to the q equals x, then it must be an element of fq. This is an if-only if statement. If an element is in fq, then it equals its own qth power. And if it equals qth power, it's in fq. This is a very, very useful relationship and sort of the basis of Galois theory of finite fields. So, armed with this, we are able to construct a new isogeny, a new endomorphism of an elliptic curve E over fq. We define the so-called Frobenius endomorphism, fr sub q, mapping from an elliptic curve to itself. And what are the coordinate functions? They are xy maps to x to the q, y to the q. So it just raises each coordinate to the power of q. Now, one thing you might want to know is this actually a well-defined map? In the sense that if I take x and y, which I assume to satisfy the defining relation of the elliptic curve, i.e. y squared equals x cubed plus ax plus b, is it true that x to the q and y to the q define a point on that curve? Do they satisfy the same relation? Well, let's plug it in and try it out. So we plug in x to the q and y to the q into our defining relation. So I've just rewritten it as trying to take the difference of the two sides and set it equal to 0. So I've got y to the q squared minus x to the q cubed plus ax to the q plus b. So we want to see that this equals 0. Okay. So here is where we use these two facts at the very top of the screen. On the one hand, I know that a and b are both elements of fq. That's the field over which E is defined. So they equal their own qth powers. A is a to the q, b is b to the q. Here I can just rearrange the indices. So y squared to the q, x cubed to the q, x to the q. And now, using the additivity, look, everything here is raised to the power of q. So I can just pull that outside the brackets. This is the magic of working in positive characteristic. Because remember, q may be a prime power. Q may not equal the characteristic is p. But because q is just a power of p, you just apply this relation however many times. If q is p to the n, you just pull out the p n times, and that pulls out the q for you. So now we are left with checking that y squared minus x cubed plus ax plus b to the q equals 0, but the thing inside the brackets we assumed equals 0. We began with the point xy on E. So this map, x goes to x to the q, y goes to the y to the q. This, because we're working over a finite field fq, actually defines a map from E to E. Moreover, it's very easy to read off the degree of this map. The degree of the Frobenius, well, just look at the degrees of these polygons. It is just Q. So it's just a degree Q map. Unfortunately, it is not this word separable that we said last time. It is an inseparable morphism. What that means is if you tried to look at the kernel of this map, and you said, okay, well, how many points are there in FQ bar, such that when I raise them to the power of Q, I just get this origin point? And the answer is, well, you have to start with the origin itself. Nothing else will work. So we don't get the kernel is size Q, as we might have hoped if it were a separable morphism. But nonetheless, we can calculate its degree. That's a useful thing. Okay. So this is an example of an endomorphism of an elliptic curve. What we'd now like to do is relate this to counting points. Here's where we might notice this relation seems pretty useful. Knowing that x to the q equals x is equivalent to knowing that x is an element of fq. Well, I have an elliptic curve. I want to calculate the number of fq points, or indeed fq to the m points. I want to know how many points there are so I can build my zeta function. But the Frobenius map will be very helpful for this. So the Frobenius is an inseparable morphism. Its kernel is somehow not very useful, viewed as a set of points. The set of points of the kernel is not very useful. However, if we don't look at the kernel of the Frobenius, but rather the fixed points of the Frobenius, something interesting will happen. So if E is an elliptic curve over a finite field FQ, the FQ to the M points, by the previous observation, are precisely the FQ bar points that are equal to their own mth iterate under this Frobenius map. So think about the case M equals 1. Frobenius Q of Z, so Z is a coordinate xy. So this is precisely asking x to the q, y to the q equals xy. And we know that happens precisely when x and y are both elements of fq. And it's true for, because q is any prime power, so a power of q is just another prime power, so the same thing is true. With q to the m, then you will be living in fq to the m if you equal your own q to the mth power. So this gives us a way to specify the points, the set of points over a particular finite field. And because it's sometimes nice to think of things as kernels, you can view this as saying that the q to the n points are precisely the fq bar points of the kernel of the difference of the multiplication by one morphism, i.e. the identity map, minus the mth iterative of the Frobenius map. Now remember, addition and subtraction on elliptic curves is not just coordinate-wise. So when you think about this map, 1 minus the Frobenius, don't think of that map as xy goes to x minus xq to the m, y minus yq to the m. Taking the difference to 2 points is something complicated. In particular, 1 minus the Frobenius, it should not be immediately obvious what the degree of this map is. That shouldn't be immediate. The degree of this map is not immediately obvious. But nonetheless, this is a way of expressing the fq to the m points of our elliptic curve. And although the Frobenius is inseparable, 1 minus the Frobenius is in fact separable. So, again, this is like, if you think of this like a derivative condition, and 1 being the map, like x goes to x, that has derivative 1. So if this has some sort of, if the Frobenius is a vanishing derivative, the derivative of this difference should be 1. So that's why you should feel like this is separable. And now we can count points. If I want to calculate the number of fq to the m points, well, I've now identified that as the size of the fq point set of this kernel, which is precisely the degree of this map. So another reason why you might not think this degree should be an easy or obvious thing. The degree might be complicated because it's at least as complicated as the point counts the elliptic curve. And if any of you did go off and do a bunch of sage experimenting after I suggested it last time, you'll notice that the point counts elliptic curves, there are all sorts of things. Well, we know they're somewhat controlled. That's kind of what we're getting at with our Weil conjectures. But they certainly can vary substantially. So this is complicated, but it's useful. All right. So we've talked about maps of elliptic curves, and we've related that to counting points. What I want to get into now is trying to find some sort of linear algebraic gadget, something like a lattice or a cohomology or homology theory, on which we can find some matrices that are capturing something related to the point count. So to talk about that, we're going to talk about the torsion points of an elliptic curve. So what are the torsion points of an elliptic curve? So we go back to our multiplication by n endomorphism. So this is taking a point and adding it to itself n times. If I look at the kernel of that endomorphism, that is called the set of n torsion points of the elliptic curves. The points such that when I add them to themselves n times, I get 0. Now, I'm not sure if this picture is large enough to be viewable on everyone's screens, but this is precisely what Masood was hinting at last time. Well, not last time, I meant a few slides ago. That if you think about what is this map doing at the level of a complex elliptic curve, you think about the picture for a complex elliptic curve. This picture is just off Wikipedia, by the way. This is an example of what the multiplication by 4 map would look like. Well, if I take this elliptic curve, so the elliptic curve is the complex numbers modulo this lattice generated by this omega 1 and omega 2, and I multiply by 4, what does the kernel look like? Well, certainly 0 is in the kernel, but also anything whose fourth multiple lands inside the lattice is also in the kernel. So omega 1 over 4. That's a point on the elliptic curve. That's a non-zero point in the elliptic curve because omega 1 over 4 isn't in the lattice. But you multiply it by 4 and now it is. Similarly, 2 omega 1 over 4 and 3 omega 1 over 4. So we have 4 points here, which is, again, as Masood was saying, you can think of these as kind of like living on a circle. It's kind of like the 4th root of unity on a circle. We have the same thing in the other direction of the lattice. Things whose, when you multiply by 4, you get something that's a multiple of omega 2. And then all the sums of such things, which will land somewhere else in the lattice. So in total, if you look at the kernel of the multiplication by 4 map, you see the kernel is size 16. And that is indeed the degree of the map. If you write down the defining polynomial equations for multiplication by 4, you will see that it is degree 16. So here is that statement just written in formulae. The n torsion is precisely 1 over n times the lattice. So elements of the lattice now with a 1 over n at the front. Because when you multiply by n, you land inside the lattice. And we're still working in our quotient space, so that's that space, quotient the lattice. Which, after you make a choice of basis, is isomorphic to z mod nz squared. So again, it's a size n squared thing. This picture we've sort of stated over the complex numbers, but it is in fact true in many situations. For an elliptic curve over any field, as long as n is not divisible by the characteristic of that field. So for instance, if you're working over fp, you do not want n to be divisible by p. So if n is not divisible by p, then the same is true. You can make some choice of basis that makes the n torsion points of your elliptic curve a finite group. I guess I should say the k-bar points of that. This is, again, some sort of scheme. But if you look at the k-bar points of that, you get a group, a finite group isomorphic to z mod nz squared. Now, you do have to be careful if n is divisible by p. For instance, if you want to calculate the p to the n torsion, that is a, frankly, beautiful story. It gets into all sorts of things, p-divisible groups, formal groups, p-adic Hodge theory is in this direction. Lots of fun stuff, but far beyond what we want to talk about. If you want to, I'm not proving this theorem, but one way one might believe it to be true is if you believe that you can calculate the degrees of all of these spaces and believe that it's separable, then you say, okay, the n torsion is degree n squared. So I expect, so the multiplication by n map is degree n squared. So I expect the n torsion to be size n squared. And I also expect a sort of chain of subgroups for every divisor of n. So I need a finite abelian group of order n squared, such that for every divisor, I have a finite abelian group of order d squared. And essentially, as a consequence of the fundamental theorem of abelian groups, finitely generate or even finite abelian groups, that will tell you that this n torsion just has to be exactly this. Right, as a product of cyclic things, and this is the only one that has the right subgroups of the right orders. So this is something that we can do for any elliptic curve. We can look at the n torsion. This is sort of a linear algebraic thing. Z mod nz squared, sort of like a two-dimensional module over z. Well, it is a two-dimensional module over z mod nz. But obviously, we've sort of made some choice of n here. This is a finite thing, so it's only capturing a certain finite amount of information. What can we do to get more out of this? What we're going to do is we're going to take an inverse limit. Doing that constructs a gadget called the Tate module. So what we're going to do is we're going to pick a prime L. So you pick some L, a prime number, and you look at not just the L torsion, but the L to the n torsion, L to the power of n, for each power of that prime. And you take the inverse limit over all of those. These possess maps, one each down to the next. And you can take an inverse limit, and doing that creates a gadget called the L-adic Tate module. Once again, you can look at the points of this, and you get, well, what are the points of each of these? As long as L is not the characteristic, the points of these are L mod Z mod L to the nz squared. And the inverse limit over Z mod L to the nz is the L-adic integers, ZL. So the L-adic Tate module is going to be, after choice of basis, isomorphic to ZL, the L-adic integers squared. Now, if you haven't played much with inverse limits or L-adic numbers, don't worry too much about it. We're not going to go deeply into the precise properties of these. But what you should think is that this is some sort of, again, linear algebraic object. This is a module over a ring, ZL. that's capturing quite a lot of the information of our elliptic curve. Once again, if you looked at...
So Angus, L is a prime.
Yes.
Here? Okay.
Yes,
so
I guess I didn't say that.
L is some prime number.
L is a prime number, yes.
And instead of just looking at the L torsion point, we're looking at all L to the n torsion points for all n. So this n is not the same n as the last slide, but
no, it's not. Yeah. So this now, yeah, on the previous slide, n is on this slide L to the n. So yeah, they're different. So the torsion here is L squared, L cubed, where L is some prime. So 5, 25, 125. You look at those torsion points, and you get finite groups of those orders squared.
So we fix an L and look at all L to the n torsions
Correct.
on our elliptic curve, and put them all together inside this module, this thing.
Exactly right. Yeah, exactly right. So this module maps to all of these, maps down to each one, and it's capturing every single one of them in one big package.
And I guess you're saying it's a module because it's a module over ZL squared, right? Well, I mean, you've written that it's isomorphic to ZL squared, which is true, but it's not canonically isomorphic, but it's a module over ZL.
Yes, I'm just saying that. So yeah, I just wanted to the module. It's a module over ZL. So in that
over ZL, sorry, yeah.
Linear algebraic information. And you're right, this isomorphism is certainly not canonical. You have to make a choice of basis. Good point. Much like the previous isomorphisms that we wrote down about the finite level ones were non-canonical. So this construction gives us a rank 2 module associated with our elliptic curve that we can define over any field. We do have to make a choice of prime L here, but we'll see that for what we're interested in, that choice of prime L will be remarkably not relevant. Quite surprising that should be the case. Everything we will do will be essentially independent of L. Now, the important thing is that if I have a map of elliptic curves, if I have an isogeny, well, because this preserves the group structure, it will induce a map between the torsion points for any L to the n. Because you just sort of pass it through. If L to the n kills your element, then I can take it outside, and that should still be 0. So L to the n better kill the image, and vice versa. So we get a map between the L to the n torsion for each n from any isogeny, and thus any map between elliptic curves induces a map, which we'll call phi L, between the L-adic Tate modules. One other thing is just, again, in the complex case. So if I look at that particular case, I'm looking at an inverse limit over L to the n torsions, but we've identified the L to the n torsions precisely the sort of L to the n root of the lattice. But this, again, at some point there's a choice of basis in here probably, but if I look at the points that L to the n multiples of them live inside the lattice, what I get is an object that simply that lattice tensored with Z mod L to the n Z. And now the inverse limit over n is only touching this sort of factor. And so I just get the original lattice now tensored over Z. I guess the basis should be Z. Maybe that's obvious. With the L-adic numbers. So this
maybe some comment is that if you are looking at elliptic curve over rational numbers, then they don't need to have torsion points, non-trivial torsion points, right?
Yes. So
over finite fields, they always have, well, except from characteristic P, they always have the expected number of torsion points somehow.
Yeah, so I've been maybe a bit sloppy here when I've written down things like the Tate module is equal to ZL in the same way. I'll go back to the previous slide for a second. And I commented here that this notation is a little sloppy. What I should be saying is that En, the n torsion, is some subgroup scheme of the elliptic curve. And then if I look at the points of this, if I look at the k bar points of this, of the algebraic closure, then I get Z mod n squared. So as noted, if K was the rational numbers Q, what this is saying is that if I look at the Q bar points, look at the points over the algebraic numbers, then I will see all the torsion. But if I just look at the rational points of this, then I may not see all the torsion. The rational points of the elliptic curve may have smaller n torsion.
But over finite fields, do we see it already at the rational level?
No, a similar thing can happen. You can have, for instance, like if you look at the points over a finite field, that's a finite set. So it certainly can't have n torsion for arbitrary n, because the n torsion for arbitrary n is very large. So again, the statement is true that if you're working at the algebraic closure, you see all the n torsion for n prime to p. But for a finite field, specific finite field, FQ, you may not see all of this. Good stuff. Thank you. All right. So we've built up a lot of what we need. We have maps between elliptic curves. We have this idea of degree. We have this idea that this might help us count points. And we now have a sort of candidate linear algebra object, because maps between this tape module are going to look like 2x2 matrices. They will now have L-adic entries, but that's fine. It's a 2x2 matrix. So we can look at a map of elliptic curves. It induces some matrix on this rank 2 module. And we can ask, what sort of information does this track? And the next thing that I'm going to tell you is a very, very big theorem. A lot of things I've said, maybe I could sort of give you a blustering sort of appreciation for by saying, oh yeah, it's more or less this. But the next theorem requires substantially more effort, and I'm hiding a lot by not proving it. So the next theorem is the following. If I have any elliptic curve and an endomorphism of that elliptic curve, phi from E to E, we saw on the previous slide, this induces a map, phi L, from the L-adic tape module of E to itself. So phi L is some 2x2 matrix. Then the determinant of that matrix equals the degree of the endomorphism. This is totally remarkable for many reasons. On the one hand, we have a degree of an algebraic function. On the other hand, we have a determinant of a matrix. And somehow these are equal. Also notice in this equation, there's an L on the left and no L on the right. Somehow this quantity, this determinant, is completely independent of the choice of L. For any L-adic tape module, you pick any prime you want, different from the characteristic, and you will get the same determinant of the induced map, no matter which L you pick. Now,
maybe a comment here about the whole theory. You know, is that in all of algebraic geometry, let's say if you work over a characteristic P, to do anything, you have to choose a different prime L. And then the answer is expected to be independent of L, but proving that is actually, in general, very hard. So that's sort of a theme that persists.
Yes. Absolutely. We will see this happen in great generality. There'll be whenever we work, we'll want to generate some sort of linear algebra object. And to do that, we will find ourselves necessarily choosing some auxiliary prime L, and we'll cross our fingers that it's the case that the choice of L didn't actually matter. Independence of L is a big thing. It's very surprising this should be true, and it sort of hints at a lot of really deep things. There's, you might look at this and say, well, okay, somehow this never mattered which L I picked. These were all true for every different ZL. So maybe there really should have been some object defined over Z. There should be some sort of Z lattice associated with my elliptic curve over a field that's doing the same role. Maybe there's some sort of integer Tate module that doesn't rely on a choice of prime L. Now, no such thing can exist directly. You can't literally write down a rank 2 Z module that captures all the information that you want to capture, that, you know, maps on the elliptic curve, induce maps on this rank 2 Z lattice. No such thing can exist. But thinking along those lines and thinking about L independence leads to a beautiful world of objects called motives. So that's way beyond anything we're doing here, but it's a wonderful, wonderful story if that is something that people find interesting. This particular theorem is also a wonderful story. And if you want to learn more about that, I highly recommend Silverman's book, The Arithmetic of Elliptic Curves. This is one of just the all-time beautiful, wonderful books in number theory and algebraic geometry. I've spoken to many people, and I've told a lot of people that if you want to become a great number theorist or a great arithmetic or algebraic geometer, step one is to get a copy of Silverman's book and read it, do the exercise, read it seriously, go through things, make sure the examples, check out, do some exercises. It's a big book, it's quite difficult, but you get through it and you say, wow, that was great. Get to the end, close it, and then open up page one and do that again. And then do that again a few more times. And if you've done it enough times, you are a great mathematician. This book has everything in it. Every time I've needed to learn something, it's like, oh, this is just some analogy with something about elliptic curves in Silverman's book. It has everything. I love this book. So highly recommend. And he gives a very thorough proof of this fact and shows you all the ingredients that you need to prove that the determinant of this matrix equals the degree of the map that induces it. The key thing is the existence of something called a Weil pairing, which is a certain bilinear form on the Tate module. So there's some way to sort of pair up the L torsion of the elliptic curve in a way that gives you this bilinear alternating non-degenerate pairing. And the existence of that is useful for showing this. Not only is this true, a sort of neat corollary of this relationship is the following. It's a sort of thing you can just expand out and check that if I have a 2x2 matrix F, the trace of that matrix can be computed in the following way. The trace of F is 1 plus the determinant of F minus the determinant of I minus F, where I is an identity matrix. So that's just a sort of fact about 2x2 matrices. Just expand out these things and check that it is indeed the case. Or if you like, you can view these all as like elements of the characteristic polynomial. Like the determinant of I minus F is the characteristic polynomial evaluated at 1. And then 1 is like the lambda squared term, the quadratic term. The determinant is like the constant term. So you subtract off this and you get the middle term, which is negative the trace. So if you swap around 1 plus the term minus this characteristic polynomial, you get the trace. So that's a nice thing for 2x2 matrices. And so using the theorem, a corollary is that the trace of this matrix phi L is 1 plus the degree minus the degree of the identity function minus phi. So there is one thing to be said here, that the map taking a endomorphism to an induced matrix is a ring morphism. So it plays nicely with things. So 1 goes to identity matrix, differences go to differences, so that's all fine. But again, not only is this determinant independent of L, so too is this trace. Very nice.
Angus, can I ask some stupid questions?
There are no stupid questions, so I'm afraid you'll have to ask some intelligent ones.
Well, you may reassess that statement in a second. So it seems like I could construct this Tate module for any algebraic group scheme. Is this theorem, that appears in Silverman's book, is there something unique about elliptic curves that enables you to construct this Weil pairing, or is this a statement that's true more or less for any algebraic group scheme and its Tate module?
Good question. So we do need a little bit more than just being an algebraic group. We also need it to be commutative, so that you do have these multiplication by n endomorphisms. So it has to be a commutative group for that to happen. And once you have that, you can certainly define this. You can define the n torsion. You can define the Tate module, as you say. And in fact, Weil pairings do exist in more generality than just elliptic curves. One way to generalize this is to say, okay, well, what if I look at the space of projective varieties because we said elliptic curves you can think of as projective curves with group structures. That's one way to specify an elliptic curve. Projective varieties in higher dimension with group structures give you a category called the category of abelian varieties. So abelian varieties are projective varieties in arbitrary dimension with group structures. And it turns out for them, almost everything we're doing today is exactly true. Now, some of the things we do today, as you can see here, sort of rely on the fact that things are 2x2 matrices, this tape module is two-dimensional, these maps are degree n squared. That's not true in higher dimension. So certain tricks that we're using won't follow, but the general ideas will. There are tape modules, and you can do most of this for abelian varieties as well. So yes, this does generalize. There are Weil pairings on any abelian variety.
Thank you. Thank you.
Yeah. So I'm afraid you failed. You did ask an interesting and insightful question. So try harder to be stupid next time. Okay. Okay. So we are in prime position to do everything we want. We wanted a linear algebra object where some sort of matrix could be related to point counting an elliptic curve. We've set up everything exactly how we need. Let's do what we wanted to do. So what we're going to do now is we're going to look at the Frobenius map on the elliptic curve and ask, what is the characteristic polynomial of the induced map on the L-adic tape module, where L is any prime different from the characteristic P. So L, again, the choice of L doesn't matter as long as it's not P. We defined AQ, this quantity from last time, 1 plus Q minus the point count. And the theorem states the characteristic polynomial of the induced map of Frobenius is precisely t squared minus AQT plus Q. Aha, where have we seen that before? What do we need to compute? Well, we compute the determinant to get this constant coefficient. And the determinant, by the previous theorem, is precisely the degree, which is equal to Q. So that's good. For the linear coefficient, we need to calculate the trace. Well, we use this sort of corollary of the previous theorem to say the trace of this matrix is 1 plus the degree of the map that induces it minus the degree of the identity minus that map. And remember, earlier on, we discussed how 1 minus the Frobenius is a separable map. Therefore, its degree equals the size of its kernel, which we said is precisely the number of FQ points. So the trace of Frobenius is 1 plus the degree of Frobenius, Q, minus the number of FQ points, which is AQ. And thus the characteristic polynomial is exactly what we want. So what we needed was we needed to get some numbers, some complex numbers, W1 and W2, so that the point count on the elliptic curve was precisely 1 plus Q to the M minus W1 to the M minus W2 to the M, looking at the FQ to the M points of the elliptic curve. But we've set everything up that this is just immediate from knowing this fact. Once you have the characteristic polynomial, basically we'll just redo that calculation we did before and see that exactly we get what we want. So W1 and W2 we take to be the roots of this characteristic polynomial of Frobenius. T squared minus AQT plus Q. Take the roots of that. Like factor it as T minus W1, T minus W2. Then, via an analogous calculation to way back at the beginning, we'll see it's exactly giving us the point count in the elliptic curve. If I look at the number of FQ to the M points, we said that's the same as the degree of 1 minus the mth iterative of Frobenius, which, by our earlier theorem, is the determinant of 1 minus the mth iterative of the induced matrix of the Frobenius. But this is just the characteristic polynomial of that mth iterate evaluated at 1, which is precisely 1 plus Q to the M minus W1 to the M minus W2 to the M as desired. And hence, we've done it. We have exactly the form that we wanted. This shows that the zeta function of the elliptic curve is exactly this rational function. Because we said that if you have this expression for the coefficient, well, just unpack it. Write out as a sum of things, exponentiate, you get all those factors, multiply them together, and you get the numerator and denominator of the rational function that you expect. So we're done. Mostly. Because I said there's two parts of this, right? One part was let's do all the work to build our zeta function to get the irrational function that we expect to get. And this does that. We have got the rational function. We have proven rationality. We have proven the functional equation. We have proven the relationship with the Betti numbers. What we don't have is the Riemann hypothesis, which in this context, remember, was saying that the size of W1 and the size of W2, these are complex numbers, their absolute values should be exactly square root Q. That's what we want to show. W1 and W2 are complex numbers whose absolute value is square root of Q.
So maybe, Angus, it's good to just summarize to say that to prove all parts of the Weil conjectures except the Riemann hypothesis part, all that one needed in the case of elliptic curves was to find the right sort of module on which the Frobenius acts. And well, what is the right words to say? I want to summarize.
I would say the main thing that we definitely needed was this theorem here, the relationship between the determinant of the induced map and the degree of the map on the elliptic curve. Once we had this, once we had some sort of linear algebra gadget, in this case, the Tate module for the elliptic curve, and we had this relation, then essentially everything else was just a formality.
Exactly. But I want to say the words so that, later when we talk about Weil cohomologies, I can refer to these words. And this theorem is too specific to elliptic curves. So I want to say that, all we need is a module together with action of Frobenius that, satisfies the right properties, but I don't know exactly what the right properties should be. Like what is,
sure.
What do you think we should
Maybe
say?
The right thing is we need to find something whose characteristic polynomial of Frobenius is related to point counts. That's what we really need. We need the characteristic polynomial of the Frobenius to be closely connected to point counts. There's many ways to achieve this, and we'll see some of the tricks that a Weil cohomology theory provides to us. But if you can get the right characteristic polynomial, then everything besides the Riemann hypothesis will fall out in a fairly formal way.
And I guess that's also, if we believe that Frobenius is acting on that module in a correct way, then the fact that its characteristic polynomial has the fixed point, that can be motivated from like Lefschetz fixed point theorem.
Yeah, exactly right. Yeah, exactly.
So eventually we will make everything formal on the existence of, cohomology theory with the Frobenius, with the right Frobenius on it, everything except the Riemann hypothesis. Yeah,
exactly right. So we will definitely talk more about this in the future, but if you have a well-developed theory of, L-adic cohomology, of appropriate Weil cohomology theory, then this theorem is exactly an instance of the Lefschetz fixed point theorem in that setting. Somehow we want to say the fixed points of some map, the Frobenius, is related to some sort of alternating sum of traces on cohomology. And it will turn out that for the case of elliptic curves, the 0th and 2nd cohomology are sort of easy. And then the middle cohomology, the first cohomology, is the interesting one. The trace of Frobenius on that cohomology, closely related to the trace of Frobenius in the Tate module, it'll turn out, which we've kind of seen an instance of that, right? We saw that for complex elliptic curves, the Tate module is closely related to the lattice, which is the first homology. So you can see instances of this already popping up. And the same sort of thing is happening here. We've got the AQ, the trace of Frobenius on this thing, which will turn out to be closer to the first cohomology elliptic curve. So something similar will happen in general, but we'll have more complicated cohomology theories going on. Good. Yes. Okay. So we have the zeta function, everything besides the Riemann hypothesis falling out of this appropriate linear algebra theory, which we will see is going to be generalized by some sort of cohomology. The Riemann hypothesis is hard, but in this case, it'll turn out that it'll fall out from a very clever little trick. So what have we got? We have a quadratic equation, t squared minus aqt plus q. And the two numbers that we need to look at, W1 and W2, are the roots of this quadratic equation. So think about this as a quadratic equation over, say, the real numbers for a moment. Imagine you've drawn your parabola on the axes. And the question you want to ask is, how many roots does this quadratic have? Does it go through the x-axis twice, once, 0 times? Well, here's the trick. Let's take this polynomial and evaluate it at a rational number m over n. Well, remember the definition of this quadratic. This is the characteristic polynomial of our matrix induced by the Frobenius. So evaluating m to the n is the same as taking the determinant of m over n times identity minus this matrix. And then, because it's a 2 by 2 matrix, we can take out a factor of n squared, and I get determinant of m times I minus n times the Frobenius. So I've just taken out one factor of n, and that's come out of the factor of n squared from the determinants. But this numerator now, mi minus n Frobenius, this makes sense as a map that's induced by a map of elliptic curves. This is multiplication by n minus the composition of multiplication by n and the Frobenius. So this numerator determinant is equal to a degree. But the degree is just some positive number, or non-negative number at least. Degree is some number. The denominator is some number that's non-negative. So this quotient is a non-negative value. Therefore, this quadratic, this parabola, is non-negative for every rational number. In particular, it's going to be non-negative for all real numbers as well, because of the density of the rationals. So we have a parabola that either is above the axis or just touches the axis. What we deduce from this is that this quadratic equation either has a repeated real root or it has a pair of complex number roots, but because its coefficients are all integers, those complex numbers have to be complex conjugates of one another. So either W1 and W2 are equal and multiply to Q as real numbers, or they're complex conjugate numbers that multiply to Q. In either case, what we find is that the absolute value of those numbers has to be the square root of Q, as desired. So the Riemann hypothesis is true via this clever trick about the non-negativity of this quadratic over the real numbers. This trick, you should not expect to have any nice generalization. All of the earlier stuff, building the zeta function, we are hoping to generalize that just by building a clever theory of linear algebra. Precisely, it'll be the theory of cohomology when we get to that. But this trick, this is pretty special. We're going to need some very different styles of tricks to try and prove the Riemann hypothesis in general. It's a hard thing. But that is it. That is the Weil conjectures in full for elliptic curves.
So can you remind me again exactly what is the statement of Riemann hypothesis?
Of the Riemann hypothesis?
Yeah.
Yeah, so what the Riemann hypothesis says is that once we have our zeta function, for each I up to 2 times the dimension, we get some polynomial factor of your rational function pi. For even I, it's in the denominator of the rational function. For odd I, it's in the numerator. Each of those pi we then factor over the complex numbers, and we look at their roots. The Riemann hypothesis here says for pi, the roots should have all absolute value. They should all be complex numbers of specific absolute value q to the I over 2. In this example, P0 and P2 were sort of easy. They were 1 minus T and 1 minus QT. The tricky one was P1 in the numerator. And we've now seen that it holds for that P1 as well.
Great, thank you.
Of course. Good stuff.
So maybe a comment that this is, of course, a very nice proof, but it's ahistorical in a sense that well, the case of elliptic curves was proven in the 1930s by Schmidt and Hasse and them, and not using these methods. I mean, Tate came up with Tate module after the definition of elliptic cohomology was given. And so this is all looking through the lens of what one already somehow knew, but not historical. Right? But this is the right way of looking at the problem, but it's not the historical way. That's the that's all. I wanted to say.
Do we have a copy of, like, I don't know if it's worth trying to find a transcription or translation perhaps of Hasse's original work? Do we have something like that on the website? Because that could be interesting. I've not read it myself. I've only read this treatment, which again comes from Silverman's book. I don't know I don't know what the historical approach would have been.
Well, first Schmidt proved the rationality and functional equation using Riemann-Roch. So he had to develop Riemann-Roch for curves over finite fields.
Yes.
But the Riemann hypothesis for elliptic curves was, proved by Hasse. I don't know. I don't remember how he proved it. But it doesn't seem like anybody sort of repeats that proof, except in some historical surveys, because somehow this proof is so much better.
It's a very
right proof.
A very slick proof, this one, yeah. I will say one, so maybe I can say one thing about the history, and in a way an application of this. So the Riemann hypothesis is closely related to something called the Hasse-Weil bound. So, or in the case of elliptic curves, something just called the Hasse bound. So on the one hand, given the Riemann hypothesis, if you calculate the size of this AQ, which recall is the difference between the size of the elliptic curve and just the quantity 1 plus q, well, AQ is just the sum of these two roots W1, W2, and so by the triangle inequality, it's less than 2 root q. So this is called the Hasse bound. And there's a version of this for curves in general of higher genus called the Hasse-Weil bound. The remarkable thing is that a sort of converse is true. Knowing this bound is actually enough to know the Riemann hypothesis, i.e. that each of these is size root q. Because if you know this quantity, if you know that AQ is less than or equal to 2 root q, well, similar kind of style of trick, we calculate the discriminant. Why is that a 2 there? That should be a q. Sorry, that's A script q there. That's an odd typo. Then we calculate the discriminant of our quadratic. We get AQ squared minus 4q. But because of this inequality, that is strictly non-positive. That's a weird, strictly non-positive is a weird thing to say. It's non-positive. Again, from which we deduce the same thing. We either have a repeatable root or a pair of complex conjugate roots, and we get the Riemann hypothesis. So the Riemann hypothesis is equivalent to the Hasse bound. So it's possible that in Hasse's formulation, he just proves the Hasse bound, which is equivalent. But as I say, I haven't actually read Hasse's work directly. That's a good point. All right, how are we doing time-wise? 5 more minutes? All right, so let me just... this is essentially the end. I just have some sort of sundry notes on what a generalization might look like and some applications. So let me just show you those. So a lot of words in this slide, but just to give you a sense of what happens in terms of generalizing. So we've said some of this already, that most of the Weil conjectures were a fairly formal consequence of the properties of this Tate module. And we should not expect that arbitrary varieties have a group structure or a Tate module, as Joe pointed out. But abelian varieties, these higher dimensional analogs of elliptic curves, do have associated Tate modules, and you can emulate much of the proof in that setting. Weil was the one to prove the Weil conjectures for abelian varieties. So you can go through things in that way. Having done that, you can then move to the case of higher genus curves. So curves beyond the elliptic case. These have an abelian variety associated to them called their Jacobian variety. And you can use the relationship between the curve and the Jacobian to prove the Weil conjectures for curves in general. This was Weil's strategy. Weil proved the Weil conjectures for curves by first proving it for abelian varieties and using the Jacobian. Now, for varieties in general, well, as we've mentioned, we have to go deep into the theory of L-adic ethyl cohomology, developed by Grothendieck. And this is, well, a big theory. But once you set it up and you have all the nice properties that it has, most of the Weil conjectures, rationality, functional equation, relationship with the Betti cohomology, this all just sort of falls out. I'll just read the last sentence. Go.
Angus, I just looked up, and apparently Hasse actually, well, he looked at Frobenius operator on the whole endomorphism ring of the elliptic curve.
On the endomorphism, okay.
So that's closely related, of course, to the Tate module, but it's not. Tate module is a more specific part, I guess, of the endomorphism ring.
On the endomorphism ring. And the Frobenius is an element of the endomorphism ring.
He looked at the Frobenius as an element of the endomorphism ring, and then he showed that the norm of this endomorphism has the right properties. I don't know, and then apparently that implies the Weil conjectures, but why that is, I don't know. Anyway, I can send you this historical thing that I'm looking at.
That'd be great, yeah. If it's, we can put that on the website if people would like to see that, perhaps. But yeah, so most of the Weil conjectures fell out nicely, but the Riemann hypothesis, the statement about the size of the roots of these polynomial factors, that was a piece of genius of Deligne. Took a lot more to get to that point. All right, we have a minute or two for some applications. So let me quickly run through these. If you go back to the world of elliptic curves over the rational numbers, these have an associated gadget called the L function. So the L function can be defined via an infinite product, kind of like an Euler product for the Riemann zeta function. And for the primes, for the primes of so-called good reduction, we have that this Euler factor is just this characteristic polynomial of Frobenius, or the P1 on the zeta function of the elliptic curve over Fp. And then a consequence of the Weil conjectures is that this expression converges for complex S with real part greater than 3/2. So I'm just claiming that's an exercise. Think about the convergence of the Riemann zeta function and see if you can deduce a similar statement by simply knowing this. Now, this isn't perfect. I haven't told you what happens at the primes of bad reduction, but for convergence purposes, there are just finitely many of those, so you needn't worry about them. Primes there are only finitely many bad primes. Almost all primes are primes of good reduction. So that's one cute application. Another is an application to cryptography. So elliptic curve cryptography, one of the things that's important is to be able to calculate the size of the FQ points when Q is a really, really large prime or prime power. So this might be just an enormous quantity, and it's just how do you practically compute it? Well, one trick is to say, we know that it's 1 plus Q minus AQ, and AQ is bounded in a certain range. So it suffices to calculate AQ mod L for a collection of primes L where their product, I'm missing an L here in this symbol. This equation should have an L before the greater than symbol, which product is greater than 4 root Q. Because if you know A modulo L, you know what modulo all the products by the Chinese remainder theorem. And if that product is larger than this, and you know that A is only so large, then this congruence actually uniquely determines AQ and thus the point count. And this is a really important step of something called Scope's algorithm, which calculates the size of this set. Oh, 3:31. I'm so sorry, but I've got a minute over time. That is bad behavior. Thank you all for your patience, and that's everything for this week.